Good afternoon, everybody. I hope that you guys are having a great start to your Wednesday or have had a great start to your Wednesday. Today is June 4th. It is Wednesday. We've got our first exam on this upcoming Monday. Um, for that exam, I'm going to be posting a couple more things for you guys to look at. Just kind of elaborating on some learning objectives to give you a little bit better sense of, the sort of questions that I'm going to ask. You'll have your quizzes um, to look at as reference materials. In addition to that, you'll have your problem sets as reference materials to look at. Um, so I'll throw some questions out there for you guys, some kind of like supplementary questions of sorts. And then I've got office hours tomorrow, 12 to 1. I've got office hours Monday, 12 to 1. Anytime you want to meet, feel free. Just send me an email and I can try to make that happen. Um, so let's just go ahead and kind of anticipate that. I want you guys to do well on this first exam to just kind of, it's always comfortable, to get a good grade on, it's always good to get a good grade. But it's always nice to have that sort of I don't know, confidence builder. Are there any practice exams? Um, no, not at the moment. I'm working on one and I'm hopeful that I'll be able to get it up before the end of the week. I was going to kind of leave that as a little bit of a not necessarily surprise. Um, but yeah, kind of a surprise. No worries. Um, so that's why I was going with, oh yeah, I've got some questions for you. So I'm going to try to get a practice exam up, and the only or what I do whenever I write a practice exam is I want to write a practice exam that kind of goes in line with your actual exam. Because if I pulled one from a previous semester or something like that, I there might be some questions where you're like, what the heck is this? Why does you're talking about sugars? And the reason that I say that is from time to time, whenever I teach this class, I kind of rearrange things. And this class is in going through kind of a transitionary phase. So I'm rearranging things kind of on the fly. No, not on the fly, but semester to semester. So I haven't really found my groove on this is the sequence that I want to teach it. Um, so anyway, long story short, I'm writing your actual exam. I'm also working on the practice exam simultaneously. I like that to be a something on Canvas so you can look at it and have, if you're taking your exams remotely, you can have that sort of simulation. But long story short, yeah, I am aiming to get a practice exam going. It might not be the full same length, which your exams are going to be 40 questions. It's not going to be, it might not be the full same or the full thing, but I want to at least give you a scale representation of it or kind of a model of it. Um, so with that, I think we'll go ahead and get cracking. What we've been talking about most recently is we've been talking about protein structure. We talked about primary structure, which is just the sequence of amino acids read from the N termini to the C termini, which is stabilized by peptide bonds, which are an example of a covalent bond. Then we talked about the next level of organization, the local structures, your secondary structure, which is stabilized by backbone hydrogen bonding. And then we get onto the tertiary structure, where we're actually interested in the amino acids, the R groups, and how they interact with one another. Lysine interacts with an arginine. Well, how is that possible? They're both positively charged residues. So that's an interaction that's unlikely to happen. However, if you switched it to lysine and a glutamic acid, ooh, that's a combination that would have an ionic interaction with one another. We talked yesterday about protein folding and unfolding, going from the an unfolded state to a folded native state. And that state or that shape is also commonly known as a conformation. And that 3D shape is three dimensions. Then after that, we talked about a specific protein. And if you remember yesterday, we kind of ended our discussion with looking at one particular pair of proteins and one particular like functional not group necessarily, but one functional class of proteins. And that functional class of proteins was the oxygen binding proteins. Now, the important thing about your oxygen binding proteins is that this is simply a model. So essentially, what I mean by that is we're using myoglobin and hemoglobin as our proteins. Those proteins will bind to oxygen, a ligand. Now, this is a model because let's say that after this class you decide to, you want to pursue research and you get an opportunity to work in a research lab where you're studying, um, let's just go with the general concept or the general term of, let's see, metal binding proteins. Let's say that you wanted to get involved in research that focused on soil decontamination. Basically having, what are some of the enzymes that are in plants that are responsible for sucking like lead out of the soil? So phytoremediation is what that's known as. So you're remediating soil and you're using enzymes to do it and proteins to do it. Now, if you were to do that and you were studying, oh, well, this protein binds lead 2 plus ions. Cool, that's great. What we're going to be looking at today, you would be able to use that as a model for and model it after oxygen binding proteins because that protein is going to bind to a lead ion, just as hemoglobin binds to a oxygen molecule or myoglobin binds to an oxygen molecule. Now, the fundamental difference between hemoglobin and myoglobin is based on their structure, but that's also related to their function. So if you look in the lower right-hand corner of your screen, you'll see that hemoglobin, or HB, is a tetramer. Now, an important part about hemoglobin as a tetramer is it's got four of these things right here. One, two, three, and four. Those are all prosthetic groups. Heme is the name of that prosthetic group. And that prosthetic group coordinates an iron ion, which enables hemoglobin to bind to oxygen. Now, myoglobin has the same prosthetic group. That prosthetic group uses Fe2 plus. That Fe2 plus is going to help myoglobin bind to oxygen. So both of these proteins, myoglobin and hemoglobin, will bind oxygen. Now, the challenge of it is, well, what makes them different? Well, the basis is that, or the simplest explanation as to what makes them different is hemoglobin as a tetramer has four O2 binding sites, whereas myoglobin, a monomer, has one O2 binding site. So hemoglobin is going to bind four oxygens, whereas myoglobin will only bind one oxygen. Now, does that mean they behave differently? It does. What it means is that the nature of the binding is going to be a little bit different. Um, you know, if they were to act in the exact same way, hemoglobin would basically act as a vacuum and suck up four oxygens at once. Spoiler alert, that's not what happens. Myoglobin, yeah, it does, because it's only got one to bind. Okay, now here's our model of myoglobin. With one heme group, iron represented by this magenta ball, and then O2 right above it. Every single one of these, it's kind of grayed out, but every single one of these numbered balls here is an amino acid. All of these amino acids fold to make a local structure of a bunch of alpha helices to the point that myoglobin and hemoglobin, for that matter, the or myoglobin and the hemoglobin subunits, individual monomers, they are approximately 90% alpha helix. So that's kind of that brings back some of our older stuff and it brings some of the more contemporary stuff that we've talked about, and it helps us move a little bit forward. Now, with that in mind, I think that one of the tough things about this class is tracking the information that we've learned and kind of using it as a needle that we thread throughout the class. Amino acid structures are very important. Understanding the classification of different amino acids is very important. Whenever I mentioned amino acid structures first, I first presented to you guys the polar charged residues. Your three polar positives, which are lysine, arginine, and histidine, and your two polar negative residues, which are aspartic acid and glutamic acid. I mention those and I stress those because arguably those are the most interesting. That's a personal preference, but what we'll see more times than not is because they can adopt a positive charge or have lone pairs of electrons, they're involved in a lot of different things. Now, to visualize that, let's take a look at this. The molecule that you see on the left-hand side, this ring structure, this multi-ring ring, is known as a porphyrin ring. So this molecule right here, I'm going to scribble out all this nonsense. It's not actually nonsense, but I'm going to scribble out the stuff that we don't want to look at right now. That is heme. Now, as a little bit of a, I always like to reference this because it's helpful for me to put it in context. Heme is something that you have a little bit of familiarity with. If you've ever sustained a bruise, like, I I swear it's like it's not necessarily once a month, once every 2 months, I will walk past my bed and I will either jam my toe, it's of course my little toe because somehow that's the one that decides to get hit, or I will slam my shin into the edge of my bed. And the bed is like the platform is like wood, and so that's really good, especially when it's dark and my wife and or kids are asleep. And so then I just go like this. Now I bring that up because what immediately happens after I like come back to reality, what I will begin to see over the course of the next few days is a bruise develop. And that bruise will go through a couple of different colors. It will go from like a dark brown to kind of a green, and then it will get a little bit lighter until it dissipates altogether. That is this molecule heme breaking down. Now, this is so this heme metabolism, heme breakdown, and heme synthesis is something that you will talk about in 4385, should you take that, which is your metabolism class. Or if you go on to medical school or PA school, you'll talk about heme metabolism. In particular, my wife and I just had a baby back in February, and he was kind of jaundiced. And so that meant his skin was particularly yellow. He had a very high heme concentration. He was a premature baby, and it's a little bit more common for premature babies to have that. He was only about 3 weeks early, so but it's more likely to happen in premature babies or babies that don't go to full term. Um, so he had heme, an elevated level of heme in his body, and what we had to do was we got this, it's called a Billy blanket, and it's basically like a blanket that we wrapped him in, and then it had fiber optics, and it sent blue light and basically tried to break down, expedite or accelerate breakdown of that excess heme in his body. And that's something that basically he has so much heme in his body that his liver couldn't keep up with that metabolism. So we were using the light source to help out. I know whenever I was born in 1983, the treatment was like, oh, put your baby in front of the window. And I mean, that's still something that people will advocate for, but it and will do, get your baby outside. But of course, it has to do with the magnitude of the or the severity of it. Thankfully, he's doing all right, and he just kind of wrapped him in the blanket for like 10 days, for a couple hours a day, and his heme started to break down. Now, that molecule is in a high abundance in your red blood cells because it is helping out with hemoglobin transport oxygen. Now, I'm going to show you. So the way that I always kind of visualize this molecule is if you look right here, here's one ring, a second ring, a third ring, a fourth ring. At those rings that I've circled, I want you to recognize this atom right here. And I know that, there we go. That atom is nitrogen. What do we know about nitrogen and kind of nitrogen's preferences? One thing that we know about nitrogen is it likes to do this. It likes to have three bonds and a lone pair of electrons. Okay. Now, if you look at some of these nitrogens surrounding this ring, this one, those both have, well, they have three bonds going back to the ring, and then they've got this guy right here. This other nitrogen right here that I'm going to put an underline by, it's got a pair of bonds going to the ring, and then this right here. My point in bringing this up and referencing this is because we've got some kind of resonance stabilization going on with this ring, but more importantly, each one of these nitrogens has a pretty high probability of having a lone pair of electrons, which makes it really good at holding something in place. That's something that it holds in place is an iron 2 cation. So with these lone pairs of electrons on these nitrogens, that iron's like, fantastic, this is where I love to be. So when you look at this ring structure right here, it's kind of hard to visualize because we're on two dimensions here, but visualize this ring D and ring C as being kind of closest to you. And visualize that you're looking at this heme molecule on this plane. So in the center of it, just as the center of my palm there, that's where my iron ion is. Now, right below that iron ion is, and I'm going to give you a second to, and good, I don't have the answer to the question that I'm about to ask explicitly on my PowerPoint presentation, but right below that iron ion, we've got this funky ringed amino acid because this right here, if you look, NCC, this is an alpha carbon going to CH2 and then a five-membered ring. Could anyone add the single letter code for this amino acid right here? I'll give you a little bit of a hint. It's a polar positive residue. Drew, correct. H for none other than histidine. What do we know about histidine? Histidine in that the ring that histidine has is known as an imidazole ring. And that imidazole ring can either be positively charged or when it's deprotonated, it's neutral. And when it's neutral, what does it have? Aha, an LP, a lone pair of electrons. So we've got a bunch of nitrogens that are holding that iron ion in place and basically kind of facilitating that iron ion from being in a particular location. Now, with that in mind, that iron ion, that Fe2 plus, what it's going to be great at is capturing our O2. Because if you think about O2, we got lone pairs of electrons on each oxygen there. So that iron ion is going to be really good at basically holding that O2 in a particular location. Now, I know that I kind of threw that at you and then asked you this right here about this amino acid at the bottom, but what we're looking at effectively is, well, this is a snapshot or a zoom in of the heme ring at basically this one right here. We're taking this model and going from this to rotate it. So now we're looking at that heme ring on its flat plane. Iron ion in the middle, O2 above it, and below the iron ion is a histidine, and above the iron ion is, lo and behold, another histidine. So we've got two histidines that are extremely important in the positioning of O2 and the iron within the heme ring. Now, with all of that said, if we didn't have this heme ring, that iron ion's not going to be positioned very easily. If that iron ion isn't positioned very easily or very well, well, then that O2 is not going to be positioned well. So I kind of alluded to this yesterday with the prosthetic group, the heme ring. It's a prosthesis. It gives our protein an ability to do something that otherwise the protein would not have. Now, essentially what that means is, or one other component of what that means is that all around this whole thing that I've drawn, well, that's part of the protein that's kind of positioned around that ring. Now, it is important that we have Fe2 plus because think about this. Fe2 plus wants how many electrons to get back to a neutral charge or a neutral state? Two. Okay. Now, Fe3 plus, how many electrons does it want? Three. Think about if you have Fe2 plus pulling towards one electron. It's got, I hope you guys can follow me on this. It can pull with 2 units of strength. Fe3 plus, if it's pulling an electron, it's pulling with 3 units of strength. So Fe3 plus, it's going to be pulling more. And if you think about the size of those two ions, let's see, Fe2 plus is an iron ion. So let's imagine an iron ion the size of this microphone here. It loses 2 electrons, it's going to get smaller. Is Fe3 plus going to be smaller or larger than Fe2 plus? Absolutely, it's going to be smaller. And by virtue of it being smaller, it's going to occupy less space in the middle of that ring. So do you think that that ring structure is going to be the exact same if there's an Fe3 plus ion in there as it would be if there was an Fe2 plus ion? Not at all. So Fe2 plus is essential basically for keeping everything kind of in its proper location. So Fe3 plus is hazardous to O2 binding, and therefore it's hazardous to kind of your health. Now, we used O2. We like O2. I like O2 a lot. By comparison, CO, carbon monoxide. I don't like that. Now, when I think about carbon monoxide, well, I think about, that's sometimes considered to be a silent killer because it has no odor and it can ultimately kind of suffocate people. Now, one thing that's important to know is that this model that we're looking at, I'm going to write out here, heme plus, and just for the sake of simplicity, I'll say myoglobin. It would be the exact same if it was hemoglobin. But just for simplicity's sake, I'm going to say heme plus myoglobin. If I isolated heme and I said, okay, well, you've got two options. You're a purified heme with iron. You can either bind O2 or CO. Okay, this is isolated heme, so in the absence of the protein, in the absence of myoglobin, this will be a little bit of a downer because what heme is going to have a preference for is carbon monoxide. And when you're dealing with purified heme, it has about 20,000 times the affinity for carbon monoxide as it does for O2. Now, whenever you change this and you say, all right, myoglobin, heme, and the Fe2 plus, and you say, okay, well, you can either bind O2 or carbon monoxide. You've introduced the protein. So you've got basically something that's going to be wrapped around that heme. Well, spoiler, myoglobin or hemoglobin and heme still have a greater preference for binding carbon monoxide than O2. Now, I bring that up because I think that most folks have heard of carbon monoxide poisoning. If you have any gas appliances in your home, definitely need a carbon monoxide detector. The reason for that is a very small amount of carbon monoxide is much more deadly, or sorry, myoglobin and heme will go after that carbon monoxide with a greater affinity than they will for O2. So it's almost like that carbon monoxide outcompetes for the binding to heme. I just bring that up because the difference between them is ultimately, well, carbon monoxide. Notice how this O2 here is at a little bit of an angle. Carbon monoxide does not have that angle. Instead, carbon monoxide shows up like this and binds straight down. The reason for that is because carbon monoxide, well, it's got a dipole, a partial positive on that oxygen, on that carbon, and a partial negative on that oxygen. The oxygen being more electronegative is going to pull to a greater force towards that iron. Whereas in O2, well, you've got two elements that are, or two atoms that are equally electronegative, and so it kind of ends at that little angle there. Now, your takeaway from this is I want you to know Fe2 plus matters. The positioning of Fe2 plus in the center of a heme ring matters. Nitrogens are kind of all around as a part of the heme ring or as a part of the nitrogen that's right below iron or above the O2. Despite those nitrogens, and despite our kind of ideal preference of O2 to bind to heme, there is an affinity difference that heme and myoglobin in heme and hemoglobin in heme have for carbon monoxide, which is why carbon monoxide is hazardous. Now, this is kind of a depiction of what it looks like when oxygen has bound to heme. What that kind of, or what I want to imply there is that, well, it's not always bound. And if you think about kind of the life cycle of hemoglobin, it picks up oxygen in the lungs and then deposits it in the tissue. So at some point, there's going to be heme molecules that don't have any oxygen bound to them. Now, what that looks like is this right here. Deoxyhemoglobin. Here's our histidine that is below our iron ion. Our heme ring, notice how it's almost a little concave. It's got kind of a downward tilt to it. That iron ion is being pulled, basically, or it's positioned a little bit down, kind of puckered toward the histidine ring. Now, what happens whenever oxygen binds? Can you tell me what happened to the histidine ring, this porphyrin ring structure, or this imidazole ring? And just look at this in terms of, that's not a straight line at all. Look at your page straight across. What happened to the heme ring? Or sorry, the histidine ring. And I'm asking that open-ended question because I'm finishing lunch. You're absolutely right. Well, it got pulled up. Whenever O2 is added, I'm looking at transition from A to B. Well, iron gets pulled up by the oxygen, and that sets off basically a sequence of events that leads to this histidine ring going upward. Now, with that in mind, um, is this, oh, this is still a part of a polypeptide, isn't it? Yeah. So that's still a part of a protein. So do you think that if that histidine ring moves at all, do you think, give me a number or a letter? Give me a number if you think, yes, other parts of the protein will move, or give me a letter if no, this is isolated, no other part of the protein will move or change. Perfect. What happens is that histidine ring gets pulled up a little bit. That histidine is connected to the polypeptide backbone, which causes other parts of our protein to undergo a slight change. Now, to visualize that, we've got this right here. This blue tube right here represents our polypeptide backbone of our hemoglobin subunit. Whenever oxygen binds, the iron ion is pulled up. What that causes is our polypeptide backbone, now represented by this pink tube, will shift up as well. The O2 binding pulls the Fe2 plus into the porphyrin ring plane, pulling the what's known as distal histidine. I want you to remember that term, distal histidine, or distal as being the histidine that is below our iron ion. It's pulled up and its helix, or along with its alpha helix, because remember this polypeptide or this whole protein is like 90% alpha helices. Now, these changes have a butterfly effect. And if you're unfamiliar with the butterfly effect, it's a movie starring Ashton Kutcher. It's also kind of a chaos philosophy, but I'd prefer to just narrow it as it's a movie starring Ashton Kutcher. Anyway, the point is, or domino effect, I suppose everyone knows dominoes. This polypeptide, it changing position causes every other part of the protein to change position, which that's one subunit. How many subunits does hemoglobin have? 4. When one moves, are the others just going to be like, whoa, I don't know you? No, they're going to be like, what's going on over there? Maybe I should. If one subunit binds oxygen and does this, I've raised my arms, I'm one subunit. The other subunits are kind of like they're a part of the crowd and they're going to be like, hey, should we? I'm going to stop right here. I don't know what's going on, but I'm going to move just a little. Not a whole lot, but just a little. Now, that is a phenomenon known as allostery. So, Allostery. Allostery is the term that's used to describe proteins that have basically two different shapes. And whenever I say shapes, I also mean conformations. You have maybe heard the term allosteric effect. If you haven't, we're going to talk about it a little bit. Now, allostery is basically the idea that a protein has two different states. In this case, when we're talking about hemoglobin, it has one state known as deoxyhemoglobin. Do you think that deoxyhemoglobin is the active or the inactive form of hemoglobin? Add a number if you think that it's the active, and a letter if you think that it is the inactive form. That's right. This is the inactive form. This, when it comes to allosteric proteins have two general identifiers. Your inactive form is known as the T state, or it's referred to as being a part of the T state or in the T state. Now, the way that I remember being taught this was T stands for, and I can't remember what it actually stands for in any sort of literature, but the instructor that I had, I remember said, well, T stands for tense. Think about yourself when you're super tense and you're like, ugh, you're not active. You're instead just like, I can't move. I don't want to do anything. The other state is the R state. That's the relaxed, it's the functional state. Now, watch these two different slides. Here's our deoxyhemoglobin represented by blue. I want you to watch, kind of get a holistic view of the protein. I'll give you a couple of seconds to look at it again so I can finish part of my lunch. Now, Let's look at the R state. The differences. Okay, give me a letter if you agree that yes, there are some differences, or a letter if you say no, nothing. The color of them does not count. Okay. So as long as you agree that there are some differences, we're in a good place. Now, if you believe that the differences are dramatic and oh my gosh, how could you not see the differences? Put a letter down. If, however, you look at them and you say, like, those differences are kind of subtle, put a number down. Okay. I would I would go ahead and say that these differences are very subtle. In order to, I think, see some of the differences or make the differences a little bit more obvious, I'm going to give you a couple of places to look. Looking at the T state, I want your attention to be drawn to the exact center of this tetrameric protein. And just so you guys can see, there's basically two proteins in the foreground. Those are the darker shaded ones, and then two in the background. This is a tetramer. Now, it might be helpful if you put like your thumb up to the screen and say like, "Oh, okay, the length of that or the width of that opening is roughly the length of like mostly my pinky." Okay? Leave your hand there. Now we're going to our R state, our relaxed or our active state. Did that central cavity's size change? It did. And if it didn't, well, then maybe you moved your hand back or something like that. My point is that yes, you should have seen that it did change. It didn't change by a dramatic amount, but it changed a little bit. Now, as a little bit of an aside, one of the things that I think about whenever I look at these T and R states is I've watched entirely too many trash TV shows, particularly ones about like plastic surgery or something like that. And one of the things that I've noticed on all these plastic surgery shows is that the plastic surgeon will say something like, well, if I'm doing a facelift or something like that, the movements that I make are going to be less than like 6 millimeters. Very, very small movements that produce a dramatic difference. They produce a dramatic effect. The same thing goes with these proteins. The central cavity of a hemoglobin protein from its inactive state to its active state, that might be a matter of 3 angstroms, which an angstrom is smaller than a nanometer. So we're talking about a very, very small amount, but it has a dramatic effect on the function of the protein. Now, with that in mind, the question is, well, how and why? And I want to do a couple of things. One, I want you to be comfortable with that term allostery. Allostery meaning different shapes, T state and R state. Now, the next thing that I want you to think about is what is happening at each one of these subunits is we are getting this movement, which is causing one subunit to shift, which then allows or facilitates another subunit to bind to O2, which causes another movement, and then another and another. So every single one of these subunits will go through this right here, causing this deoxyhemoglobin to transition to look like this right here. And you can kind of see if you look at beta 1 in the upper right hand corner, you can see where that heme molecule is. And then, oh, yeah, it did move a little bit. Okay, so with that in mind, we're going to go through a little bit more about hemoglobin and kind of what its functionality is. The binding of O2 to the Fe2 heme complex alters the electronic state of the complex, which causes a change in color. Deoxyhemoglobin and hemoglobin absorb light of different wavelengths, which I have a Garmin, let's see, Forerunner 945, and it's got a pulse oximeter. It tells me approximately what my blood oxygenation level is. And if I remember correctly, that which is also on like an Apple Watch, essentially that percentage, if you've ever gone to the doctor or a hospital or something like that, they put the thing on your finger and it says, oh, your blood O2 saturation is about 98%. Good. You're breathing well. You're getting lots of oxygen in your bloodstream. That's awesome. That's effectively looking at the ratio of your oxyhemoglobin to deoxyhemoglobin. You want to have a lot of oxyhemoglobin. And this is wavelengths. Ooh, that's within the visible light spectrum. So this instrument on my wrist is able to basically read or, send out a signal. And I think I'm going to stop right there because that's the extent of my knowledge of engineering. If I went any further, there'd be somebody who'd be like, that bozo doesn't know how a pulse oximeter works. You're right, I don't. But what I do know is that it is a ratio, or it is looking at the ratio of oxyhemoglobin and deoxyhemoglobin because they absorb light of different colors. Now, your dark purple or venous blood and your scarlet or your arterial blood is going to be kind of a rich scarlet. Now, the oxidation of Fe2 plus to Fe3 plus is one thing that will prevent binding of O2. So in the event that somehow all the iron in your body got oxidized to Fe3 plus, what's going to happen is your oxyhemoglobin is going to plummet, your deoxyhemoglobin is going to go up by comparison. What that's going to look like is Fe3 plus heme complex. It's got a different pigment to it. It's kind of a brown color. And that is known as methylmyoglobin. Now, I have a friend who went to the University of Kentucky, and he told me that there's on the eastern side of the state near bordering West Virginia, there's a population of people who are referred to as the blue people of Kentucky, not because they're tremendous Wildcat fans, but instead because through generations of inbreeding, they have this affliction, this methylmyoglobin. They have basically a myoglobin disorder that is a very strong genetically linked trait that basically gets passed down from generation to generation, and they have like a blue hue to their skin. Now, carbon monoxide, NO, and H2S can bind to that Fe2 complex, Fe2 heme complex, which is something that I alluded to earlier about the affinity that they have to O2. Okay. Now, when it comes to protein ligand binding and oxygen hemoglobin binding, or hemoglobin oxygen binding, we're going to do some math and look at some mathematical expressions. Now, the dissociation of a protein ligand complex can be written as an equilibrium. PL, what I need you guys to know is that PL stands for protein ligand. So that is our protein that has been bound to the ligand. That is a complex. Then this red P represents our free protein. That protein is not bound to our ligand at all, but it can bind to our ligand. So if we wanted to take this equation right here, or this expression, and rewrite it as an equilibrium expression, we would say Kd, or dissociation constant, is equal to the concentration of P times the concentration of L divided by the concentration of our protein ligand complex. Now, the way that you could think about this, or the way that I think is helpful to think about this, is to say, okay, well, I'm going to draw a solution. We've got PL, we've got P, L, 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 P, P. Now, what I want you to answer this question is, or sorry, that was a weird question. What percentage of protein is free protein within this solution? Let's see, we've got P. Okay, I got to vote for 50%. We've got PL, that's one protein molecule wrapped up with one ligand. We've got free P, free P, free P. A grand total of 4 protein molecules. One of them is not considered free because it's wrapped in the complex. So my question of what percentage are free protein, it's going to be 75%. Because for this, whenever I'm asking just about protein, I don't care about this, this, this. So I'm going to go ahead and write L stands for ligand. So I'm going to take this right here and convert it to our equilibrium expression. I'm going to say KD equals, and I'll just put the numbers in parentheses. I'll say 3 for proteins, and then L. How many free L's do I have? Well, I've got 4. What about my PL complex? Well, that's going to be 1. Does everyone follow how I converted this right here to this expression right here? Give me a number if you follow, or a letter if you say, wait, stop the press. Okay, great. Now that's the foundation of what we're going to be doing. In most conditions, the ligand concentration is going to be very high compared to the protein concentration. And therefore, the formation of PL does not generally change or does not change dramatically with the change in ligand concentration. Now, in addition to writing it as a KD or dissociation constant, we can write it as a fractional percent of our ligand binding sites. Okay, so if you think about, let's go with myoglobin. I always like to start with myoglobin. How many ligand binding sites does myoglobin have? Well, it's got 1. Hemoglobin's got 4, but 4 is a larger number and more complicated number than 1, so we're going to start with 1. We like to come up with this fractional percent, which is represented by theta, this symbol right here. Theta is going to be the number of binding sites occupied divided by the total number of binding sites in the solution. Okay, what that looks like, using that same terminology of PL and L, is this right here. PL over P plus PL. Okay, so I'm going to go back to drawing this kind of awesome model that I had a little bit ago. Actually, you know what I'm going to do? I'm going to switch it to MbO2. I'm going to say O2 and BO2 and 2 and MB. Okay. So if I wanted to take what I've got right here on the left-hand side and put it into this theta model, what I'm going to do is I'm going to say, all right, well, how many protein ligand complexes do I have? I've got MbO2 twice. Does everyone agree with that? Oh, just a second. So on the previous slide, okay, so what was the 75%? All of P or only free P? The 75% was only the free protein. Sorry. Are we good? Okay. Feel free to send me a message. Okay, so what we've got here is PL. Basically, how many of that PL or MbO2 complex is formed? Well, I see 2 instances of MbO2. Each myoglobin protein there has 1 binding site. There are 2 myoglobin proteins. Each one of them is MbO2. So each of those binding sites are occupied by that ligand, which is O2. Can I get a number in the chat if you follow that, and a letter if, wait, I don't follow? Okay. So what I'm getting at here is, I'm going to get the highlighter out. Myoglobin has 1 binding site. This myoglobin that I just highlighted has a binding site, and it is occupied by O2. This myoglobin also has 1 binding site, and it is occupied by O2. In this kind of circle that I drew to represent my solution, there are actually 3, 4 myoglobins. But whenever I'm filling in this top number, what is the number of binding sites that are occupied? So I don't care about the free myoglobin. I only care about the um, I only care about MbO2 for this number. So I'm going to put 2 there. That brings me down to, well, what about free protein? In this case, now I want to look back at this right here and say, all right, well, where do I see the free protein? Here's 1. Here's another. Well, I've got 2. Plus my PL, which is the same as this number, that's also going to be 2. So I have a total, and this is the tricky thing, I've got a total of 4 ligand binding sites. 2 of them are occupied. So if I were to take these numbers and plug them in, my fractional percent is 2 divided by 4, or 0.5. Now, let me ask you this. Did I care at all about the free O2, this and this right here? Nope, I don't. Because, well, it's the ligand. I don't care about how much ligand there is in the solution. I care about how many of my ligand binding sites are occupied. Now, can I get a number if you follow that? Great. Now we're going to kind of develop it a little bit more. So if we take our fractional percentage and we look at our dissociation constant, our this rascal right here, what we can do is rewrite our dissociation equilibrium as this right here. Why can we do that? Well, the reason is we took this equation right here, and this is a derivation. I'm just showing you guys kind of the steps. PL is multiplied by each side. So that removes it from the denominator here. Then we divide each side by KD, which gets us this right here. Which gets us, yeah, to that point. Now, with that in mind, we can take this newly found expression of PL is equal to protein times ligand divided by KD, and we can look at this fractional percentage and plug in what we've now defined PL to be. And when we do, we plug it in there, and then we plug it in there. So effectively what that enables us to do is say, all right, well, theta is equal to P times L over KD over P plus P times L over KD. Does everyone follow me to this point? Not necessarily like, oh, I know exactly why we did that, but I'm going to use the word that makes me feel like I'm 112 years old, the arithmetic. If you can follow that, then you're in a good place. What we're trying to do is make this a little bit more friendly for the purposes of graphing. So we make this substitution. This right here is what I just rewrote. Now, the great thing that I remember from Mrs. Bozeman's Algebra 2 class is whenever you get these complex fractions, you can cancel out a bunch of stuff. And when we cancel out a bunch of stuff, we end up with this right here. Theta is equal to our ligand concentration over our KD plus our ligand concentration. So we put this in terms of the dissociation constant of our protein and our ligand and the concentration of our ligand. This equation allows us to express the fractional percent of the ligand binding sites as a function of ligand concentration. And the reason that we want to do that is because arguably it's easier to track the ligand concentration than the protein ligand concentration and the free protein. If we can set up an experiment where we say, oh, right, well, this is our concentration of our free ligand, that's an easier experimental design than to track the protein, especially because if you think about these oxygen binding proteins, here's what they do. Bind. My hand is a protein. The Monster Energy drink cup is a ligand. Release. Bind. Release. Bind. Release. It's a very transient and a very temporary thing. So monitoring and determining, well, what's the protein ligand concentration right at this absolute instant? Okay, here's a complicated calculation, and oh, it's gone. It's changed because the nature of this interaction is this protein will release that ligand over time. Now, visually, when we talk about this equation, we can represent this as a hyperbolic curve. Now, how does the O2 binding to myoglobin vary with oxygen pressure? This is where we've made a little bit of a change. If you remember in Gen Chem 1, you learned about gas laws. You learned about the ideal gas law, the combined gas law, the Gay-Lussac law, Avogadro's, Charles's law, which last semester I jokingly referred to as Chucky's law. And I said, "Is that funny to anyone?" And they said, "No." I was like, all right, to each their own. Um, you had Charles's law and then Boyle's law. Well, Charles's law relates gases and they're, when you think about gases, do you measure the concentration of a gas in a solution or in an environment? Nope. You measure the partial pressure of a gas. So Charles's law basically says, well, we can equate or look at partial pressure of a gas as being equivalent to a concentration of a gas. O2 is our ligand to myoglobin. And so we want to take this right here and put it in the context that's relevant to this system. So we want to say, well, myoglobin or MbO2 produces Mb plus O2. So when we write this as our expression, we've got Kd is equal to free concentration of Mb times the concentration of O2 divided by our protein ligand complex, or in order to follow Charles's law, we've got this right here, where we have P sub or PO2, or our partial pressure of O2. Like I said, Charles's law is the quantity of gas absorbed by a liquid is proportional to the partial pressures of the gases above the liquid. So essentially, if you can determine the gas concentration or the partial pressure of a gas above a solution, it's equivalent to what it is in the solution. So that enables us to say, well, O2 concentration is proportional to PO2. Okay, that was a lot. Does anyone have any questions? If you feel good about what we've done so far, put a number in the chat. If you're unclear, give me a letter and say, could you go back to this point? Okay, great, great. Now, this is helpful, but what can we learn from our KD? Well, we use the KD to express the affinity of a protein for a ligand. In this case, we're talking about myoglobin's affinity for oxygen. Mathematically, our KD is equal to 1 over Ka. So our KD is the equivalent to our dissociation constant is the inverse of an association constant. Now, what this means in terms of KDs, and I will try to use KD or theta, is the lower the KD, the higher the affinity of the ligand for a protein. Now, one of the ways that I think about this is, and I am going to elaborate on this because this was something that I really struggled with as a student, and I don't think that I was the only, well, I know for a fact I was not the only one. And so I'm hoping that I can kind of clear the air on this. Um, and this is going to be a theme that we revisit later on. Let's say that I'm going to use the same terminology and use and quantify it. So my name is Joel. I have an affinity for, I'm going to say Frosted Flakes. I like Frosted Flakes cereal and Cinnamon Toast Crunch. CTC, we'll say. Cinnamon Toast Crunch. Yeah, there we go. Let's say that my affinity for Frosted Flakes is 0.1. I'm not going to use any units because I don't want to distract anyone on that. I feel like I'm already maybe producing a distraction by talking about cereal, but zero point 0.1. Now my um, CTC, actually, let's change this. I'll drop affinity and I'll just say my KD. So I'm using the right terminology. My KD for Frosted Flakes is 0.1. My KD for Cinnamon Toast Crunch is 0.0001. Okay. My KD for Cinnamon Toast Crunch is lower than my KD for Frosted Flakes. So what that means is if I had a bowl of cereal and I had, let's say, 1,000,000 Frosted Flakes and one single Cinnamon Toast Crunch piece, cereal, whatever they are, crunchers, my dissociation constant is so low for Cinnamon Toast Crunch that what I can do is in that bowl of 1,000,000 Frosted Flakes, pick out that one Cinnamon Toast Crunch. Because my dissociation constant is so low, my affinity is so high for that that I can just go straight in for that. It's kind of like if you ever when I was in elementary school, they brought the drug dogs to our school, not to like sniff out drugs. That was high school, but instead to like demonstrate, look at this dog. And everyone was really excited. And then what they would do is they'd be like, okay, what we're going to do is get a bunch of coffee grounds and really strong smelling things. They'd pass it around to the kids and they'd be like, one of these has the odor of marijuana in it. And the dog's going to be able to pick that out. Every person would just go, you know, whatever container to container, they'd be like, I can't smell the difference. They all smell like coffee beans. And since we were in elementary school, it was like, bleh, bleh. So everyone would do that, but the dogs would be able to detect that small amount of whatever odor, even masked in this other stuff. So you could kind of think about a dog has a KD for a drug dog has a KD for drugs that they can pick that one thing out. So the KD, the lower the KD is, the higher the affinity. Okay. Now, oxygen binding. We're thinking about protein ligand interactions, but we're thinking about oxygen binding proteins. That's our model. Now, we looked at a percent or a fractional percentage or a theta. Whenever we talk about oxygen binding proteins, we make the slightest different change. We refer to this as Y. This is the number of binding sites occupied divided by the total number of binding sites. So the math is the exact same. So that right there is the same as this right here. This Y is equal to, well, all that. Now, the fractional percent of O2 binding is also known as the percent oxygen saturation, which is the number that you get on your pulse oximeter. Y is equal to the concentration of our protein ligand complex, or MbO2, divided by free Mb plus MbO2. Now, our Kd for this is that right there. We're looking at the partial pressure of O2. Now, these two equations, what we can do is rearrange them to come up with this right here. Partial pressure of O2 over Kd plus partial pressure of O2. This is the equation that we looked at a little bit ago, but The only difference was this right here wasn't PO2, instead this was L. But Charles's law gave us the kind of autonomy and the authority to say, well, instead of PO2, I'm going to use L, or instead of L, I'm going to say PO2. Now, all of this derivation, all these calculations are super helpful for when it comes to graphing this and coming up with what's known as an oxygen binding curve. This is a protein ligand binding curve also. So what this allows us to do is look at the fractional percent of oxygen bound at a specific concentration of O2. Now, I want you guys to look at this graph and tell me, where am I going to find the concentration of O2? And I'll give you a little bit of a hint. Is it on my x-axis or is it on my y-axis? And I'll give you a little bit of another hint. It's not on the y-axis. So I think everyone can see that it's in the x-axis. Does everyone follow that right there? Okay. What we want to be able to do is we want to look at an O2 binding protein and say, all right, under these conditions, what percent of my protein has O2 bound? So when it comes to concentration of a gas or a partial pressure of a gas, we use units of pressure. For instance, torricelli or torr. If you looked at this graph, and I'm going to go ahead and say, could somebody add to the chat or make an approximation, add it to the chat, if the oxygen or the partial pressure of oxygen is 10 torr, approximately what is the percent saturation of our myoglobin protein? Oh, I like it. I like that. It didn't go with 70, didn't go with 80, 78. Okay. Miracle and Anisha, I will ask you guys to resolve your differences after class. You obviously have strong opinions and will. I'm just happy that we're not in person because you guys might be really angry with each other. You have strong convictions that it's 78. No, it's 80. It's 78. No, it's 80. It's 80. It's 78. Okay. So I like that though. What you guys did was you found 10 on the x-axis and played a little game of Battleship and just said, uh-huh, there we go. It's 79. Split the difference on you guys there. Okay. Now, what this curve tells us is basically that piece of information. Now, this is important, and this is what an oxygen binding curve for myoglobin looks like. Now, do you think, at a number if your answer is yes, and at a letter if your answer is no, do you think that an oxygen binding curve for hemoglobin will look different for that of, or from that of myoglobin? A number for yes, a letter for no. You're right. It will look different. It will look different because myoglobin is a monomer, hemoglobin is a tetramer. How different is it going to look? We'll get into that. But what I want you to take away from this is that, and you can think about this kind of physiologically, if we were right here, that's a dashed line, and that's intentionally dashed. I would say that this is approximately 2.5 torr. At about 2.5 torr, our myoglobin protein is nearly 50% saturated, or it's 0.5. That is an important benchmark when it comes to oxygen binding proteins. Now, when O2 binds to myoglobin, the binding increase is hyperbolic with the pressure increase. So what that means is that it changes rapidly and it goes up rapidly. It is not linear because at some point, yeah, it's going up very rapidly, but at some point it kind of plateaus. Now, 2 points on the binding curve are very important and they should be apparent. One is whenever it is half saturated Our half saturation point is this right here. This is an important number because this is referred to as a P50. This is an affinity constant. So when we talk about oxygen binding proteins and proteins that bind ligands, we're curious about, well, how much of our substrate or how much of our ligand do we need to give to our protein or in order for it to be 50% saturated? In this case, if myoglobin is in the environment with 2.5 torr, it's going to be 50% saturated. Suzanne, what's your question?
My question is, as we're talking about this, is this like a Michaelis-Menten plot, like Bmax, and is that like this? It's what it's reminding me of. Is this kind of the
It,
same idea, or
yes. So I'm happy that you see that because where we are going, we're talking about proteins. We're going to get to enzymes. If you've learned anything about enzymes, you've learned about Michaelis-Menten and a Lineweaver-Burke plot for enzyme activity, so converting a substrate to a product. And where you look at the maximum velocity, you also look at a constant for an enzyme. This is exactly what that looks like. So just as a little bit of a preview, this is what we're going to also be looking at when it comes to enzymes. And Suzanne, you're absolutely right. So great question. Um,
okay, great. 'Cause I didn't want to like confuse the two, but to me it seemed like you were saying they are the same, so I can just kind of read them the same way is what you're saying.
Absolutely. The
Great.
only thing that's going to be a little bit different is on a Michaelis-Menten curve, the y-axis is not going to be a measure of saturation, but instead enzyme activity or rate or velocity that it's catalyzing the reaction. But the principles of the graphs are effectively the same. So we need to know our point of half saturation. That's known as our P50. Then your point of full saturation. And this is a little bit tricky, but your point of full saturation, I mean, 1.0 is effectively 100%. I'm watching this curve, and what's going to happen is this is basically going to go on. It's not going to curve like that because I'm just not a good drawer, but it's never going to reach 100 and it's never going to reach, or sorry, it's never going to reach 1.0. It's never going to reach 100%. And the reason for that is, well, think about the nature of a oxygen binding protein. It's transient. It binds it, it releases it. And that's exactly what we want it to do. We want it to bind and then we release it. Now, P50, keep that in mind. That is important to know about it. Another thing that I'd like you to see whenever you're looking at this graph and whenever you're looking at these graphs, um, this is kind of a trap that people fall into where they say, okay, well, my P50 is 2.5 torr, which a P50 has a number and a unit. The unit is the pressure of the gas. Okay, so if my oxygen or my percent saturation is 50%, when my PO or when my PO2 is 2.5, if I double my PO2, if I double my concentration, would somebody tell me and add to the chat approximately what is the percent saturation when I double my O2 concentration from the P50 or from what the P50 is? About 60. You're absolutely right. This is not a linear relationship. So if I double my O2 concentration, that does not mean that my protein has gone from 50% saturated to 100% saturated. If it were a linear relationship, that is what would happen, but it is not a linear relationship. I want to caution you about that because that's an easy trap to fall into because it's like, oh, well, I double it, then that doubles. Not the case. Now, P50 is when our PO2, or sorry, when our O2 concentration gets us to 50% saturated. When 50% of the ligand binding sites are occupied, our KD is often called a P50. So think about a KD as a dissociation constant, but when we talk about oxygen binding proteins, it is uniquely referred to as a P50. So P50 is uniquely reserved for oxygen binding proteins. Now, what we can do with that is we can take our equation, our Y equation, and say, all right, well, PO2 over P50 plus PO2. A high P50 means a low affinity. A low P50 means high affinity. So if you have a hemoglobin protein or a myoglobin protein that has a P50, let's just compare two P50s, equals 0.01 versus 10. One of these, A and B, one of these is going to survive better in a very low oxygen environment. Add to the chat which one is going to survive in the low oxygen environment or perform better or anything like that. You're right, it's A. The lower that the P50 is, the more easily it can thrive in that low oxygen environment. Okay, so when we look at oxygen binding parameters, yeah, we're interested in theta, and theta is just kind of that Y value scaled up to 100%. Rather than being a fractional percent, we can call it a percentage, 50%, 100%. Now, when we look at these two different proteins that are represented here, well, A and B, these two different proteins will have two different P50s. If we look at our x-axis, there we go. Again, which one of these will be better off in a low oxygen environment? A or B? Add it to the chat. Perfect. A. Now, there we go. There's our P50 that I just drew. And then here's our other P50. Stronger binder versus a weaker binder. The binding is considered weaker when it takes a greater oxygen concentration to reach that half saturation. Now, one of the things that I want you to recognize about these and be comfortable with this terminology is going to be revisited when we talk about Michaelis-Menten curves and enzyme reactions. There's an oxygen binding curve like this can shift to the right or it can shift to the left. I say that because, well, A, if it were if it were to shift to the right, if you were to say something like an oxygen binding curve shifts to the right, that means the P50 increases, so its oxygen affinity goes down. If I were to ask you a question about graphs A and B or data sets A and B, what I would say is something like, how could A basically look like B? And I would want you to say, well, it could shift to the right. Don't say it shifts up or it shifts down. Oxygen binding curves shift to the right or they shift to the left. We'll see some more application of this in a little while. But this is all what we need to know about myoglobin and an oxygen binding curve or a myoglobin and oxygen binding curve. Now, to bring it back to our context of hemoglobin, hemoglobin has a T and an R state. One thing that I need you guys to remember is that myoglobin does not have a T and an R state. The reason that does not is because it's a monomer. Hemoglobin, by being a tetramer, or another way of putting it is a multimeric protein, it is capable of this allosteric shift or this allostery. Oxygen binding initiates a series of movements that will result from the T to the R shift. Now, whenever I say shift here, I'm not referring to the binding curves, but instead I'm referring to the movements of parts of this protein. Now, this shows our central cavity in the T state being considerably larger than that of the R state. This also shows a couple of different groups. For instance, histidine HC3, well, this one ends up down here. This one ends up in the back of the protein. So these are some kind of dramatic shifts. The movement affects predominantly the quaternary structure of our alpha beta protomers. So those are kind of our subunits. Now, oxygen binding and our conformational change, we already kind of talked about this with respect to our ring or our iron ion ending up in the same plane as our ring. Oxygen binding causes a conformational change to occur at the heme ring. Without oxygen bound, that's represented by blue, but whenever uh, oxygen is bound, that iron ion is pulled. In this perspective, it's pulled down. Earlier, we were talking about it being pulled up. Um, what this also does is it pulls one specific histidine, that distal histidine, which is histidine F8. That is a part of our protein that causes this movement. The F helix is the helix that moves when oxygen binds. Oh, sorry. Okay, so what I want you to know here is that O2 binding causes iron to end up in the same plane, which causes as the same plane as our ring, and then our F helix is going to move. Now, O2 binding, just as I was saying a little while ago, and let's see, it's 3:20. We've got some more time. We're good. Um, O2 binding causes a conformational change in the subunit. Okay, shape change. As more O2 molecules bind, hemoglobin transitions from the low affinity T state to the high affinity R state. This is a phenomenon known as cooperativity. More specifically, it's known as positive cooperativity. I love to learn with analogies and metaphors. And what we have is we've got, I've seen hemoglobin depicted in this way. Hemoglobin has 4 subunits. And consider these 4 squares to be those 4 subunits. What is going to happen to hemoglobin is one subunit will bind O2, and then I'm going to give it kind of a curved edge. This subunit right here has bound O2. That one's going to have its F helix is going to move. What that's going to cause is kind of a ripple effect. It's going to cause these other subunits to undergo slight changes. Those slight changes will make those other subunits more capable of binding O2. Now, the analogy that I put together that I thought made sense was I remember in junior high, we had dances at my school. And one of the things that was true of junior high school dances was everyone, for the most part, would stand on the outside of the dance floor and be like, whew, I'm not going to dance. Because if I do that, then everyone's going to know that I'm dancing. And what's more ridiculous than going to a dance and dancing? I will look like the biggest fool on earth. The good thing to do is stand out here on the sidelines and let all that happen. Then what eventually happens is somebody either pushes their friend onto the dance floor or someone just says, forget this. I'm going to go and dance. And that first person out on the dance floor is like the first subunit of hemoglobin binding oxygen. Now, all of a sudden, all of the other subunits, all of the people at the junior high dance are looking on the dance floor and they're like, I mean, it's still kind of ridiculous. I'm not going to go out there. That person's out there, but that person's kind of ridiculous. The other subunits of hemoglobin are looking at the one that's bound to oxygen. And they're like, look at that hemoglobin subunit having fun. Looks like a fool. Binding oxygen like that? I mean, it sounds like it. I could. I just don't want to. And then one of the other subunits says, you know what? Forget this. I'm going to bind oxygen. Just like the second kid at the junior high dance says, you know what? That person's having fun. I'm going to go see if whenever I dance, I also have fun. And they go out there and they're like, lo and behold, I too am having fun. And then the third subunit says, I kind of always wanted to have fun. So I'm going to bind oxygen. The third junior high kid says, you know what? I was gonna go out there and dance first, but I had to get ice cream. And so I'm gonna go out there now. And by this point, the fourth subunit says, I always wanted to bind oxygen. You guys just wouldn't let me. Just as the last junior high kid is like, I always wanted to dance. I'm the best dancer. Watch me. So, what I'm characterizing there is, or what I'm trying to convey is that the affinity that each one of these subunits has for binding oxygen goes up. So, if we were to quantify this, I'm just going to say whenever we've got deoxygenated hemoglobin, every single one of these subunits has not bound oxygen. None of them want to. One of them eventually will whenever the oxygen concentration is high enough. So let's say that each one of these has a P50 of 0.001, 0.0001, 0. They're progressively lower. What happens is when this first hemoglobin subunit binds oxygen, the P50 that this one has right here goes up. Or sorry, the P50 goes lower. The P50 goes lower. So its affinity for binding oxygen increases. Then when two oxygens are bound, well, then this other one now all of a sudden really, really wants to bind oxygen. This one really, really, really wants to bind oxygen. Does that make sense? So this is known as positive cooperativity. As one subunit binds the ligand, every other subunit now has a greater affinity for binding that same ligand. Now, what we see when it comes to a oxygen binding curve is this right here. So what this is trying to illustrate is overall, what does a hemoglobin binding curve look like? I mean, overall being from a deoxygenated hemoglobin to a completely saturated or completely oxygenated hemoglobin. Our high affinity, known as our R state or our active state, versus our low affinity T state. Our protein will transition from the T state to our R state, and that transition is represented by this right here. Think about this as our third and fourth O2 binding. That is what the P50 for those third and fourth oxygens is. This is basically our first. Then this is for our second O2. So if you wanted to simplify this, and I think a good way to simplify this is to say the first O2 has the highest hill to climb to bind to hemoglobin. The third and fourth is most easily bound. This is known as positive cooperativity or cooperative binding. The observed oxygen binding curve is going to have this middle shape, also known as a sigmoidal curve. This is something that is uniquely seen in multi-subunit proteins. So this binding curve, which I'm going to put a big star over, that binding curve right there is unique to multi-subunit proteins because they have this kind of progressively increasing affinity for the later substrates or the later ligands. This is not what myoglobin is going to display because myoglobin, well, it's one subunit. It binds one O2 molecule. So cooperativity, oxygen binding changes the myoglobin and hemoglobin conformation, but we don't have a T and an R state because we're not undergoing this allosteric change in myoglobin. In hemoglobin, adjacent subunits, affinity for oxygen is going to increase. This is known as positive cooperativity. Now, this figure right here captures our deoxy hemoglobin and our oxy hemoglobin. So our deoxyhemoglobin has the lowest affinity for O2. Our oxyhemoglobin has the highest affinity for O2. Yeah. And what I'm going to do today is I'm going to stop right here. So we're stopping at slide number 24. We've stopped at cooperativity. What we're going to do tomorrow is finish this up, and we'll also start on our discussion of enzymes. If you look through this PowerPoint, there are some things that are kind of newly presented, but then lots of things are kind of, well, let's continue and add upon this idea of hemoglobin and what makes hemoglobin kind of unique. We'll talk about this Bohr effect, which is a very important thing to understand, and basically ionization, allostery. We'll talk about a couple of different things, and we'll talk a little bit more about hemoglobin and its function within the body as a O2 and a CO2 transporter. Everything that I'm scrolling through right now, I'm going to be talking about tomorrow. Notice, and just to kind of stress, like, hey, we're revisiting things that we're talking about today. This figure at the bottom, we're looking at that central cavity of hemoglobin. How is that central cavity of hemoglobin impacted by something? I'm going to leave it vague as something, but if you look at the top of the slide, you can figure out what that something is. Um, and it's just more oxygen binding curves. So it will be important for you to understand what an oxygen binding curve does, knowing a shift to the right or shift to the left. But we're stopping at slide 24. We'll pick that up tomorrow. I've got office hours starting at 12 p.m. tomorrow. If you want office hours before then, just let me know. Um, Other than that, though, I hope you guys have a great afternoon. And I will stop my recording and hang around for a little bit. I just want to get all the way back to slide number 24 so then I can. There we go. That's where I stopped. I'm going to stop my recording. Have a great day, everyone. If you want to hang around, you got some questions, feel free. See ya.